We'll now check the Havriliak Negami analysis function with a couple of examples. We'll start by loading the data of a theoretical simulation. In this case, we'll press the load new file. I'll say that the format in this case is the CPRP format, which is the format that I define for my data. And we'll start by analyzing, in this case, this first file. So every time we load a new file, we can choose the format of the data, and then we need to press this button here which will ask us to enter the samples dimensions. When we do this, we also have to define how many frequencies are measured for each temperature and what is the first value of frequency measured. The program has an automatic button that calculates this based on the data that you entered. For now, we will ignore the dimension of the sample since this is just a theoretical simulation. I'll press OK, and then when we press Run, the program will now calculate all the functions discussed previously. I'll press this Havriliak Negami analysis button, which will open then the windows for the Havriliak Negami fitting. I'll start by choosing the permittivity. We can make plot data. And then we see here that in this case the data that we are analyzing is a convolution or a sum of two dielectric relaxations. For simplification, we'll start with a more easy model where the relaxations are very well separated and the data is not very much convoluted. So we see here that we have the starting conditions on this menu. We need to start, before making the fit, we need to start giving the starting conditions to our software. So we can either enter the value. In this case, this is the static value of the permittivity, and we say it's around 7,000. We can either enter the value here, or we can press this button, and it will ask us for a mouse click, and we'll say that our value is around this order. So the software will calculate the point value that we entered. So now we'll enter the infinite permittivity value of the first relaxation. I know it should be around here. Now it's asking for the tau value of the electric relaxation, the lower frequency one. So we can do again the same. We'll go here to this window. It will say it's around here. Now the infinite term of the permittivity of the second relaxation, it's around here. The tau value around here, and this is the menu that allows to choose the fitting power, how many iterations we wish that software should run until converges to a solution. We'll start by putting the low value. We can choose several algorithms for fitting. I think that usually this fmin search bound or this trust region reflective work best for this type of data. We'll start using this one, and we'll press, in this case, to fit 2 picks. So as we see, the first fitting result is not very good, and we can improve quite a bit this if we start giving even more restrictions to the software. So these are quite a few parameters to fit, so we can help the software converge to a better solution if we start restricting some of these values. So in this case, I'll say that this value here, I know that it should be around here and here. So this lower part of the menu basically allows us to restrict the upper and lower bounds of all the fitting parameters. So this works for the f-min search bound and the trust region. For this algorithm, it will not work because basically this algorithm does not consider restrictions. So we'll choose again this one, and we'll say that our value should be from here to here. We'll try a new fit. It's still not converging very well, so we'll help a little bit more the software, and we'll say that our alpha and beta should be probably a little bit higher than these ones. So we'll say that alpha minimum value, let's try 0.4, beta again 0.4, we'll do the same for the 2, 0.4, 0.4, we'll try run the fit again, and we see that we are very close now to our beta solution. So now what we can do is we can load these fit results as our starting conditions to improve the next iteration fit. So we can do this by pressing this button here. We'll run again fit2pix, and as we see, we have now a perfect fit. We can see the residuals or the errors of the fit by pressing this plot residuals. We see that for low frequencies we have some dispersion. We can try, for example, to change to this algorithm. Sometimes either one gives a little bit better results. Let's try now. And as we see now, we have the residuals very low, so this fit is very good. So we can also now change to the modulus, and we can try to see if this data makes sense or no. So when we make a fit, if we, in this case, I'll change again to the permittivity. When we make this fit, we have here all the results for these parameters that we are entering here, and we have also the tau maximum and the relaxation frequency maximum for the two relaxations, and the program will also tells us, in this case, since we are working in permittivity, the program will tells us what is the relaxation frequency in modulus. So for these fitting results, we are expecting to have one peak at around 200 Hz and the second one at around 7 to the power 4 Hz. We can press here and let's take a look at if these values are agree to our data. So the first one, it's pretty close, and the second one, it's also very close. So we can now try to fit two peaks using these starting conditions, and we see that the fit it's pretty close. Let's try to load the fit results and make fit two peaks. Let's try to change the algorithm. It did not help a little bit, so let's go back. Let's try to put here fit power, and there we go. We have again perfect fit. Let's check the residuals, and as we see here, very nice fits that we achieved. So this is a first example of a more easy solution. Now let's move on to experimental case.